Dear friends, welcome to this electrical engineering knowledge sharing channel AMP Power System. We have already discussed two sessions. Session 1 we have discussed entire power system protection, and in the session 2 we have discussed about hazardous area classification and evaluation and application of various electrical and instrument equipment in the hazardous area, as well as we have discussed about the various principles on which various hazardous area electrical instrument equipments are designed, manufactured, including troubleshooting, maintenance. We have already discussed. After a short break, we are going to discuss another new session today, that is a session 3, where we will be discussing about the very basic parameters of electrical power system, which is called power factor. Most of our friends and colleagues who are already on job, they are aware of this power system parameters, that is power factor. But this video is only meant for those who are very fresh or who may be in the school or college or maybe other discipline who are want to aware or want to share their understanding about the power factor. It is especially made for all of those so that they could have a basic idea about this power factor of a power system. Before going into detailed discussion on this power factor, we will start from the basic point to have a clear physical understanding of this power factor. Now, this power factor is very important parameter in the power system because this factor decides out of total power how much power will be utilized to convert other form of work, either it is mechanical work or electrical work. By controlling this factor, we can upgrade or enhance the out of total power percentage of mechanical power or electrical power output can be enhanced. So it is a very basic and very important parameter to reduce the footprint, because at the end of the day, whatever the active power or the power which is producing work we produce out of different type of fuel, either it is a coal or it may be diesel, it may be gas, or it may be other form of energy. So if we can utilize most of the power or which is flowing through the circuit, if we can utilize or if we can increase the utilization factor, then automatically carbon footprint will be reduced. So it has another important impact on the environmental point of view. So considering all this point, we'll discuss this in details. But before going into that details, let us discuss about the basic understanding or basic physical meaning of this factor. What is this? To start with this, let's discuss from the basic point, means we want to discuss it to clear understanding. We know that electricity has a two form. One is a direct current form, another is alternating current form. I am discussing this way because then we will be understanding what is power factor. Now, in the case of direct current, we know that when we inject a voltage to a particular load, it draws some current based on the load. In the case of DC, the moment till the voltage is constant, current will be maintaining constant. The moment the voltage changes, immediately current will be getting changes. There is no time difference between these two. How is it? Suppose I have a 12-volt battery. Suppose I have a 12-volt battery connected to a resistance of, suppose this is a 4 ohm resistance or 3 ohm resistance, and it is going, it is a 4 ohm resistance. Suppose this is a 4 ohm resistance connected to a 4 ohm resistance, which is considered as a load. 4 ohm resistance connected to a battery. So how much current will follow? We know current I equals to, this is a 12 volt, so 12 by 4 is equal to 3 ampere. Okay. Now if we plot this, how is it? So this is a time. Suppose this way we are proceeding time. This way it is a voltage or current. Whatever. Now when there is a voltage, suppose the voltage is 12 volt, it is a constant over the time. Now during this time, what is the current? Current is suppose 3 ampere. This is a 12 volt. Suppose this is a 3 ampere. So this is the current. So till this voltage is constant, current is also constant. There is no change. The moment, suppose suddenly the voltage, battery voltage drop down to 8 volt. The moment voltage drop down to 8 volt means this is 8 volt, suppose this is 8 volt. At this moment the voltage changes to 8 volt. Then automatically what will be current? When the voltage 8 volt, the current will be 8 by 4, that is equal to 2 ampere. Automatically at this moment current will be changes to 2 ampere. You see from here, the moment voltage changes, immediately current is getting changes. There is no lagging or leading of the current with the voltage. So it is, we call it is in same phase. Same phase means at the same time these changes are taking place. There is no buffer or there is no lagging or leading in this case. So in case of DC, that's why we say in case of DC, there is no phase difference between the voltage and current. That is, it is a uniphase. Okay. This is in case of why I am describing this thing. So this will help us to understand the physical situation of the power factor. So in that case, we cannot define, as there is no difference of phase between these two. So there is no phase difference. We can say phase difference in case of DC, it is a 0. Except inductive and capacitive circuit, that is also during, inductive circuit, when you switch on the inductive circuit, there will be initial, there is some tangent, then it becomes fixed. So this tangent period is very small time. Similarly, the capacitive circuit or LR circuit in the case of DC. So this tangent part we are not discussing over here. We are discussing about the steady state part. Okay. Now the same thing when we are going to discuss in the AC system, then how it would be. In case of AC system, we know AC system. In the AC system, suppose the voltage and current what we mentioned, that is generally RMS current. You know the RMS current, how we calculate. It is not the actual value every moment. It is not the instantaneous value. We know the AC current. Suppose we are discussing about a fundamental frequency AC current, that is a 50 hertz supply. So in that case, what will happen? In the case, suppose there is a alternating single phase voltage connected to a resistance. Same resistance, suppose it is a 4 ohm resistance is connected over here. Suppose it is a 12 volt, same 12 volt. But here, it is the same 12 volt supply is connected over here. Now this 12 volt, it is a 12 volt, but it is AC. Now if we plot this voltage, how this is, suppose this is a time and this is a voltage. We know this AC voltage, how it will be like this. If this is the voltage profile. Now this is the plotting all are instantaneous value. If we take RMS value, we get the RMS value. Now due to this voltage, there will be current. Now in case of resistance circuit, there is no leading or lagging. So the current and voltage, it is in the same phase. That means when the voltage is 0, current is 0. Now since current, in this case, current will be looking. Suppose the current is less than, magnitude is less than voltage, but it is a same phase. This is a current and this is a voltage profile. So here, when the voltage is 0, current is 0. When the voltage is maximum, current is maximum. When the voltage is minimum, this is current is also minimum. So it is changing in the same manner and same time. So there is no difference. We are talking about the time difference of changing. So magnitude wise it is different, but time phase, in the time scale, the moment it is changes, voltage is changes, current is also getting changed. So there is no difference in case of pure resistive circuit. This is we know very much. So in case of resistive circuit, voltage and current is same, we call it is in same phase. But if this voltage, AC voltage which we are applying, if this voltage is not DC, not the resistive circuit, if the circuit has an inductance, suppose this 12 volt we are applying, single phase 12 volt, we are applying to a inductor. Suppose this is the inductor. Then what will happen over here? So here also we are plotting the voltage. How the voltage is, this is the voltage profile. Suppose this is the voltage. This is a V or I, and this is the time scale. Now here same way, this is the voltage. Now we know in case of inductive circuit, voltage and current is not in the same phase. Current is always lagging of voltage. That means when voltage is zero, current is not zero. Current will be different and it will be lagging by 90 degree. That means when the voltage is maximum, at that time current will be zero. It is a lagging by 90 degree. So in case of, if it is a time, suppose this is a equal is 1 cycle. In case of 1 cycle, is a, if it is a 50 hertz supply, 1 cycle means 20 millisecond, right? So in this case, what is happening? So in this cycle, this is total is 20 millisecond. So in 5 milli, this is a 5 millisecond, this is 5, this is 5, and this is a 10, total 20 millisecond. So when the voltage, when is the, once the voltage switched on from the zero, it goes to maximum in 5 millisecond. When the voltage reaches maximum value, then only current will start increasing. That means current will start from here. So you see, then current will gradually increasing, and current will be gradually increasing. You see here, the moment voltage switch on, the voltage will maximum after 5 millisecond. And at that time, as it is inductive circuit, current is lagging behind the voltage. How much? It is 1/4 cycle lagging. That is, we call it phase in 90 degree. In time scale is a 5 milliseconds. After 5 milliseconds, it will start increasing. Then in another 5 seconds, when the voltage becomes zero, current is maximum. This is the current maximum. Then when it is minimum, then the current is again zero, and it is going to the reverse direction. And when the voltage is zero, current has become negative maximum. So this is, we say it is a 5-second difference between the voltage or current to changes. It is not like a DC or AC resistance circuit, as the current and voltage was changing at the same instant. In case of inductive circuit, it is not changing in the same way. It is changing, current is changing with the voltage after 5 millisecond in case of 20 millisecond cycle AC supply. That means 50 hertz supply. Replaced by capacitor, then this will be leading by 90 degree, means current will be leading of voltage by 90 degree, means 5 millisecond. When voltage is zero, current is maximum positive, okay, by 5 millisecond difference, okay. It is zero and this becomes zero at 5 millisecond. So these were in the capacitive circuit. So, but if this circuit is combination of these two, then how much this difference will be changing? If this circuit has a both resistance and inductance, then this angle, this time will not be 5 millisecond, it will be less than 5 millisecond, because because this has another impact on the system. So in case of resistance and reactive circuit, this difference of time between the voltage and current can vary from 0 to 90 degree or 0 to 5 millisecond in case of 50 millihertz. And in the case of space, if you go by space, it will be 0 to 90 degree. This is 90, it is 180, this is total. One waveform means 360 degree. Okay. So in case of alternating current, the current value when you injecting voltage is not changing at the same instant when the voltage is getting changed. It is changing with respect to time, and that time there is a difference between the voltage and current. In case of inductive circuit, current will be lagging from voltage by 5 millisecond in case of 50 hertz supply, or 90 degree in case of angle, and in case of capacitive circuit, it will be leading by 5 millisecond of voltage or 90 degree leading of voltage. But if the circuit is combination of inductance and resistance, then this 5 millisecond will be lesser. So we can say for electrical circuit, the time difference between voltage profile, voltage changing of voltage and current is not instantaneous. It depends on the combination of the load or the combination of resistance and inductance of the circuit, and depending on that, this time difference can vary from 0 millisecond to 5 millisecond in case of 50 hertz supply or 50 hertz supply. That means this is your one cycle, this is equal to 20 millisecond. So it can vary from this to this, which is in time frame it is 5 millisecond, in space form it is equal to 90 degree. How we get this 90 degree? Now we know this is very simple. That is this angle theta. We know theta equal to omega into t. T is the time. Now omega means how much? Omega is the angular frequency. Means in 1 second how many cycles it can rotate. So in one rotation it is 25 degree. If the frequency is n, then in 1 second it is rotating n times. So it will be 2 pi. One rotation means 2 pi. So n time frequency n means it is in 1 second it is rotating n times into n. So that is the angular velocity, that is equal to 2 pi n into t. Okay. Now if you go for 50 hertz, then this frequency is 50 hertz. So 2 pi into 50, and then into time. Time is how much we said? Suppose at the time of 5 milliseconds. So 5 millisecond means 5 into 1000 second. So if you calculate this, you see 5 into 10, 100, 100 and 500. So it become pi by 2, means it equal to 90 degrees. So this is a 90 degree. So in that case, in this way, we can get this angle. So in angular form, it will be 2 pi nt, means that is equal to theta. So this amount of angle of difference between the voltage and current, and it will be decided by the frequency. You see this theta value, this lagging value or leading value theta, it is dependent on the frequency of n. So if we increase the n, then automatically it will be different magnitude. That means we are discussing about the 50 hertz supply. If the supply is not 50 hertz, if there is another frequency, then the automatically angle will be different. Okay. So we can see that due to the angle, the current and the voltage, there is a different magnitude different, and again the current magnitude is not changing in the same fashion all over the time. To capture this, how much current due to this phase angle, how the current is getting affected, to discuss this thing, or how much phase angle, how much shifting or lagging or leading of the current with respect to voltage, to describe or to give a presentation of that, we define a factor which is called the phase angle. Phase angle means this is the angle in time of space, angle is theta. This theta, how much theta after the current will be changing, or how much theta ahead of voltage current will be changing. To describe this thing, we define this phase angle. So this phase angle we represent by theta. So we can see that means the voltage and current is not in the same phase. There is a difference of phase, when generally this phase is defined by theta. In case of 50, in case of pure inductive circuit, this theta equal to pi by 2. But for the combination circuit, it can vary from 0 to pi by 2, any value. So from that point, if we represent this vector in the space, then how it is? Suppose this is a voltage vector and this is a current vector. We represent in this way. So in case of inductive circuit, we say it is a lagging. So if the voltage is over here, the current is lagging by what angle? In case of 50 hertz, your inductive circuit is lagging along this way. But for the combination of inductance and resistance circuit, this is suppose angle is theta. Then how the current vector, as this is lagging clockwise, suppose this is the vector, lagging we always represent by anti-clockwise. So clockwise means this way. So this way, suppose this is a theta. This angle is theta. So this is the magnitude of the current and this is the angle. So this angle is theta when you represent in the waveform. Suppose this is a 90 degrees, suppose it starts from here. This is a theta. This angle is theta. So from here we can see that current has this current is a vector, right? We know current is a vector, is a directional element. So this current, that means this vector we can dissolve or we can regulate in a two component. One component align with the voltage. If this is the theta, we know this angle will be I cos theta, and perpendicular component will be I sin theta. We know this part. That means when there is a current I flowing through a circuit, suppose this circuit is, this is AC circuit, this is a resistance inductor and this is a resistance flowing through this. And due to this current is a vector and this is the voltage. This current is flowing through this and this is that total current, and this total current we can now dissolve in two components, as it is a vector with angle theta with the voltage. Along the voltage it is I cos theta, perpendicular voltage is I sin theta. The component, when we say in the DC circuit, when the current and voltage in the same phase, that gives a power. We know in the case of DC circuit, power we define how much voltage into current, right? Because this voltage and this current is the same phase. In the case of AC circuit, AC resistance circuit, similarly, the same formula voltage and current, because they are in phase. But in other case, because this voltage and power, it gives voltage and current, this gives actual mechanical power or heating power, actual active power, we call it active power. Similarly, in the AC resistance circuit, the voltage and current, the current component or which is along the voltage, that give the power, that give the output power, means actually it does a work. Now here you see in the same way, if we see the current, now the current is not along the voltage, one component of the current is along the voltage, another component of the current is perpendicular to the voltage. So which component will give the power to us? Only this component which is along the voltage, that factor or that component of current will give the power, actual power, or the mechanical power or thermal power. So this component is called the active current. So I cos theta component, where I is the total current in the circuit, this is the total current, this to I cos theta, this component we call the active current. And the component which is perpendicular to the I cos theta, this component we call reactive current. Okay, this component we call reactive current. Reactive current. This reactive current, in case of inductive circuit, it produces a magnetic flux or magnetic field. In case of inductive capacitive circuit, it produces capacitive charging. So this is the current resolution. Okay, so you understand we can understand from this, that means the phase angle which is lagging or leading of the voltage of the current and voltage, there is an angle between these two, we have seen in the waveform. That angle has an immense impact on the active current. So if this, we know theta value, cos theta value, it varies from 0 to -1. Okay, now we are considering 0 to 1. So if cos theta equal to 0, then this active power will become 0. That means if the current is perpendicular to this, that means if this is purely reactive circuit. But if the cos theta equal to 1, this cos theta, when cos theta equal to 1, when theta equal to 0 means when current and voltage in the same phase, then the current will be 1. So this cos theta or the phase angle has an immense impact, or it has a huge impact on the current which can produce active power. That's why this is a very, very important parameter, because the I cos theta, this will give you the active current or active power. So as cos theta, this theta can be varied how? By changing this resistance and reactance. By the combination of resistance and reactance, this is decided. Therefore, we can, by changing this combination, we can change the theta, means cos theta. So if we want to utilize most of the current, then the theta will be 0, means the circuit will be purely resistive. That is not possible. So we have to improve by reducing the reactance of the circuit, so that it can give maximum active current. So this is a controlling factor from a particular current. Okay, suppose the current is 100 ampere, and if the cos theta is 0, the circuit is carrying 100 ampere current, but it will not give any power. But if cos theta equal to 1, then it will give 100 watt power, 100 ampere current we can produce. You see, this value has a great impact on the current magnitude, which can give a power, means which can indirectly reduce the carbon footprint, means it can control the environmental condition. So it has indirect a huge impact at the end. Okay, now we'll see how this cos theta we call the phase angle of the current with respect to voltage. Okay, now we'll see this phase angle, how does it impact. This theta is called the phase angle, and cos theta we can define separately. So this theta is called the phase angle of the current with respect to voltage. It could be leading, it could be lagging. Now we'll see how this phase angle has impact on the power. That is our important thing. Now we are considering everything with respect to 50 Hz, fundamental frequency N. Now again we'll draw the same diagram. This is a voltage and this is a current. Now in case of inductive circuit, we are considering inductive circuit, current is lagging by suppose angle theta. This is the total current. Now in any circuit, in case of DC circuit, power is always volt ampere, that is a kilowatt. There is no reactive or capacitive power in the case of DC circuit. So in the case of DC circuit, power we define voltage into current, that is a volt ampere. that volt ampere equal to watt in case of DC. But in case of AC, in the case of AC resistance circuit, it is same like DC. But in case of AC inductive combination, inductive resistive or capacitive resistive, or the combination of all three, in that type of circuit, this power, when we multiply actual voltage and actual current, we get a volt ampere, and that VI we call apparent power. In case of AC inductive, capacitive or combination circuit, what is inductive plus resistance plus capacitance, or inductive plus resistance, capacitance plus any combination, that is we call apparent power, or we call volt ampere. So apparent power in case of AC circuit, first one terminology we use, we call is apparent power. Second we call is active power. There are three power we define in case of AC circuit. Active power. Third parameter we define as a reactive power. These are the three power we define in case of AC circuit. What is apparent power? Apparent power, when we multiply direct voltage and current, volt into I, we call it as apparent power or volt ampere. Okay. Now, what is active power and reactive power? Active power is that component of power which is given by the active current. Active current, which is the component of current which give the active current which is give the power, that is we call active power. And reactive current component give the power which is called reactive power. So to get the active power, what we have to do? We have to take the active component of the current, which is that means this current, we know it can be divided into two parts. One part is along the voltage, which is give the active power. So if I is this, so this component will be I cos theta, as we discussed before, and this component will be I sin theta, right? So this voltage aligned component is give the, this is active current. Active current give the power which is called active power. So active power equal to how much? It is for single phase circuit. We are discussing for single phase circuit. So active power equal to how much? That equal to similarly voltage into active current, that equal to I cos theta. So this is for active power. And the reactive power which give the reactive component of the current. So reactive power how much? This will be reactive power is equal to same voltage into reactive component of the current into I sin theta. So we can see there are three power. So now I can delete this. There are three power. One is a apparent power. In case of AC circuit, AC combination circuit, we can get three as apparent power, active power, apparent power, active power, and reactive power. Apparent power is a direct voltage into current, that is active power. Apparent power. What is active power? Voltage into current into cos of phase angle. And reactive power equal to how much? Voltage into current into sine of phase angle. These are the three. It goes for the single phase circuit. Single phase circuit. Now, in case of three phase circuit, we know how much it will be. Three phase circuit, this will be root 3 into V into I. We know this factor. And this is a three phase circuit, is apparent power. And active power will be how much? Root 3 into V into I cos theta. That is equal to active power. And reactive power equal to how much? Root 3 into V into I into sin theta. This is equal to reactive power. These are the three power factors. Now we are now discussing about this, suppose active power. So you see here the active power for this three phase circuit or single phase circuit, it is fully dependent on the phase angle. So active power for three phase circuit, if we consider active power, is equal to root 3 into V into I into cos theta. This theta is ultimately the phase angle. So that means by changing the phase angle, suppose particular current I is flowing through a line, the product of these two is a 100. Suppose V into I equal to 100. Now if the cos theta equal to 1, then this will be 100 watt. Suppose active power formula is a watt. So if we V into I, suppose the product is 100. Now if the cos theta equal to 1, that means the phase angle is 0, we get 100 watt power. But if the cos theta is 0, then how much power we will get? 100 into 0, that means 0 power. Though V into I is 100 volt amp, still we are not getting any power, because all the power is not, this power is not giving at all any work. So this factor has a great impact on the, to get active power out of the apparent volt ampere which is flowing through the circuit. Circuit is carrying current I, but ultimately we are not getting any power due to this power factor of the load. So by controlling the power, this angle cos, when this cos into theta, this factor in the power formula, when you get the active power V into I into cos theta, as this cos theta is controlling the power of the circuit, actual power of the circuit, this factor cos theta we call is a power factor, because it is deciding the how much power will flow in the circuit. Active power will flow, that means power which is producing energy or work, which is doing work like a rotating a pump or producing heat, that is a deciding by this factor, that is we call it a power factor, and this power factor is a great impact. Now this part, we have this power factor we generally call, it is for the fundamental frequency. For the fundamental frequency or fundamental supply, fundamental hertz means 50 hertz or 60 hertz, this power factor we call it displacement power factor. This is another terminology we use. This power factor cos phi we call is a displacement power factor. Displacement power factor. Okay, this is called displacement power factor, or DF. We call it displacement power, DPF. We call it displacement power factor, which is getting out of fundamental frequency. Displacement power factor we get out of fundamental frequency. When the fundamental frequency supply going through the circuit, then the circuit will give a power factor due to the combination of the resistance and reactance and capacitance, and that power factor is called displacement power factor. Okay, now this power factor is not the total real power factor, because we know that any circuit in the electrical network, it is not only carrying the fundamental frequency, especially if this electrical network contain various non-linear load. Now we are going to discuss about the harmonics impact on the power factor. That is we are discussing. So that intention of this, that why we are discussing frequency, we want to know the actual power factor of a circuit. That will be decided not only the fundamental, also if there is a harmonics in the network, or in the, if any harmonics is going through the network or through the load, then the power factor will get changed due to the harmonics. To discuss that part, we are discussing this second part. Now we know any circuit which contain a non-linear load. What is non-linear load? Like your fluorescent lamp or arc lamp, which is continually switching on off, or it may be welding transformers, okay, which draw high current with the sparking. Then it could be a converter, it could be inverter, it could be substarter, it could be variable frequency drive, which has all the solid state device which is going continuously switching on off, on off, on off. This type of switching operation produce lot of harmonics, and those harmonics will be flowing through the load or through the circuit. Those harmonics, how we can calculate the effect of these harmonics on the power factor. To discuss that part, this harmonics power factor is very, very important. Now this harmonics power factor, before going into that harmonic power factor, how we decide, this is decided by the harmonics current. In the case of harmonic current, we call this, that power factor we call distortion power factor. Now this distortion, suppose a particular supply, when the current is flowing through the circuit, pure sinusoidal frequency, this sinusoidal current, okay, this is a, suppose this is a current and this is a time. The sinusoidal will be like this, but if the current has a various harmonics, then this current will be like this. So it has a various other component. So this has a huge different impact on this circuit. To discuss this part, we have to capture all the harmonics which are present in the supply. Now how we'll calculate? To calculate this thing, we first call the distortion power factor. This distortion power factor, we define this equals to how much? Distortion power factor is defined with respect to the fundamental frequency as well as all the harmonics. Okay. Now distortion power factor is defined with respect to the fundamental. Suppose fundamental current is I1 and all the harmonics which is producing this distortion, that equals to how much? That will be I equal, it is actually called I into IRMS. This RMS due to various harmonics. The RMS current due to various harmonics, what are the harmonics current? All the harmonics current, RMS value is the divided by the fundamental current is called the distortion power factor. Now how we can define this one I1 divided by root of, you see this is equal to summation of I n equals to 1 to infinity. That means this is equal to how much? This is equal to I1 into, this is a square, by root of I1 square plus I2 square plus I3 square, and so on. So this is called the distortion power factor. Now this distortion power factor, if we multiply by the displacement power factor, then we can get this total or true power factor. But this distortion power factor we can simplify further. How we do simplify further? We can simplify the distortion power factor with another terminology. So this equal to, we can write down, so you see I1 by this equal to, we can write down, if we divide by I1, this is equal to 1 by root of 1 plus I2 square by I1 square plus I3 square by I1 square, like that. It will go like this way. We can divide this distortion power factor in this way. Now to define this further, you know, this we call one terminology THD, total harmonic distortion. This is how we define. This equal to defined by distortion due to various harmonics by fundamental. That means similarly it is defined by IRMS, but this IRMS is due to harmonics only, not the fundamental, divided by fundamental. Okay, so this equal to I square RMS, you can divide in this way. So this equal to, if you define this equal to root of, what is this? IRMS, this summation of IRMS, how much? R, you can n equal to 2 without fundamental, 2 to infinity. That means I2 square plus I3 square plus dot 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 IN square. This divided by I1 square. So if we, this is total harmonic distortion, this part is the total harmonic distortion. So if we include the total harmonic distortion in this formula, then we can see the distortion power factor equal to 1 by root of 1 plus this equal to total harmonic distortion. Total harmonic distortion square. This is equal to the formula for this distortion power factor. So now with these two, distortion power factor. Now if this distortion power factor and this fundamental power factor or this displacement power factor, if we multiply, then we get the true power factor. True power factor, which should include the fundamental as well as frequency. This is equal to how much? Displacement power factor. Displacement power factor multiplied by distortion power factor. Distortion power factor. Now displacement factor we see cos phi, that is the cos theta, into distortion power factor is how much? 1 by root of 1 plus TDI. TI is the total harmonic distortion square. So this equal to, so you can say the total power factor TPF is equal to cos theta displacement power factor by root of 1 plus total harmonic distortion square. So this is equal to total power factor. This is including all the harmonics effect. So if the harmonics is 0, if there is no harmonics, that means total harmonic distortion will be 0. Then automatically total power factor will become the displacement power factor, because this total harmonic is 0. That means root of 1 means 1 is become cos theta. But if there is a harmonics, then it can calculate all this. So this is about the power factor. So today we'll close over here. So next session we will go what is the impact of this power factor to various electrical business. That we'll discuss in the next workshop. So thank you very much indeed for joining after a short break, and let's see how we can improve our sharing of knowledge, and we'll be continuing in this way. Thank you very much indeed.